In this video, we're going to learn about the angle-angle criterion for similar triangles. In a previous lesson, we learned that two figures are similar if their corresponding side lengths are proportional. All right, corresponding side lengths must be proportional, and their corresponding angle measurements have to be congruent to each other. Okay, that's true for any similar figures. But a special case exists for similar triangles. We learned that the sum of the interior angles of a triangle will always be 180 degrees. This means that if a triangle has angles measuring 40 degrees and 80 degrees, 40 plus 80 is 120, then the third angle must be 60 degrees, since 40 plus 80 plus 60 is 180 degrees. If a second triangle has angles measuring 40 degrees and 60 degrees, then the third angle must be 80 degrees. This means that the triangles are the same shape, but they're not necessarily the same size. Okay, and when we have when we have two figures that are the same shape but not necessarily the same size, that means that we're going to have corresponding congruent angles, corresponding side lengths that are proportional, so the triangles must be similar triangles. Okay, and we can see that picture right here. All right, here's our first triangle with angles measuring 80 degrees and 40 degrees. This angle up here must be 60 degrees. And then this triangle has angles measuring 60 and 40 degrees, so this angle missing must be 80 degrees. And again, we can see that the corresponding angles of the two triangles are congruent to each other, but the side lengths are definitely not congruent, but they are similar. These are same shape, but not necessarily the same size. And this leads us to the angle-angle criterion for similar triangles. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Okay, you're going to have corresponding congruent angles, and then you could always take a triangle and scale it to be the size of the other one, meaning that, again, they're not the same size, but you could turn them into the same size by using a scale factor. So that's going to create similar triangles. So looking at this example, we have triangle ABC, and then here we have triangle DEF. And I want to know, is triangle ABC similar to triangle DEF? Just by looking at my picture here, all right, to be similar, I know they have to be the same shape, but not necessarily the same size. Okay, these are the same shape. And looking carefully, I can see that this is a 60-degree angle, and this is a 60-degree angle. Here I have a 40-degree angle, and here I have a 40-degree angle. Two angles of one triangle are congruent to two angles of another triangle, meaning that, yes, these two triangles are similar to each other. So I can say, yes, the triangles are similar. The triangles are similar since two angles in triangle ABC are congruent to two angles in triangle DEF. Okay, so since I have two angles in one triangle congruent to two angles of another triangle, that means that these triangles are at least similar. They're not congruent triangles, though, because triangle ABC is smaller than triangle DEF. Okay, but again, I know that they are similar to each other since they've got corresponding congruent angles, and then I could always take my smaller triangle and scale it so that it would be the same size as triangle DEF. These two triangles are similar. Example 2 is asking, what is the side length of DE in example number 1? Set up and solve a proportion to show your work. Okay, so if we bring back in the picture that we were working with here, they want to know how much is the measurement, the side length DE. How much is this right here? Okay, in order to do that, I'm going to have to set up a ratio of corresponding sides. DE corresponds to AB in my picture. So one ratio that I can set up is DE over AB. And looking at my triangles again, All right, on this triangle that has DE, I know side EF. EF was 8 centimeters. EF corresponds to BC, so I can use that as another ratio. EF corresponds to BC. Since the two triangles are similar, and again, I knew that because two angles of triangle ABC were congruent to two angles of triangle DEF, I know that the side lengths have to be proportional, meaning that these ratios must be equal to each other. Okay, so I'm looking for the measurement of side DE, so I'm going to keep DE there. And DE again corresponded to AB. AB in my picture right here is 2 6/10 centimeters. So I'm going to have DE over 2 6/10 equals EF, which measures 8 centimeters, over BC, which is 4 centimeters. 8 over 4. Okay, so there's my ratio, there's my proportion, I should say. DE over 2 6/10 equals 8 over 4. All right, what I can do, I can actually simplify 8/4 down to 2 over 1. So if I bring this over here now, DE over 2 6/10 equals 2 over 1. Okay, and again, I'm going to move in this direction. I want to get to the measurement of DE. So in the denominator, I want to know how did I get from 1 to 2 6/10? Well, I simply multiplied by 2 6/10. So I better do the same thing here in the numerator to get the measurement of DE. DE is going to equal 2 times 2 6/10, which is going to be 5 2/10. And the units that they used in the example were centimeters. Okay, so bringing back my original picture, I now know that this measurement for side DE is 5 2/10 centimeters. All right. Now, example number 3 wants to know what is the scale factor that maps triangle ABC onto triangle DEF in example number 1. What does this mean about the size of triangle DEF compared to triangle ABC? All right, well, the scale factor is always the value of K. All right, K represents the scale factor. And in order to figure out what the scale factor is, we take the image measurements and compare them to the corresponding pre-image. All right, image over pre-image. All right, so taking any set of corresponding sides from triangles DEF and ABC, I can come up with that scale factor. So I can show it in a couple of different ways. All right. All right, triangle DEF is my image, all right, since ABC is getting mapped onto DEF. This one is the image, and ABC is the pre-image. So if I just take any measurement from triangle DEF, the image, and compare it to its corresponding side length on the pre-image ABC, that will get me the scale factor. Well, I know EF corresponds to BC, 8 over 4. So I can take the image length of 8 and compare it to 4, 8 over 4, and that simplifies down to 2 over 1. All right, or I could have taken this measurement that we just calculated, DE, 5 2/10 over AB, 2 6/10. 5 2/10 over 2 6/10 also equals 2 over 1. And so I know that my scale factor here, K equals 2 over 1, or 2. The scale factor in this example is 2. So what does this mean about the size of triangle DEF compared to triangle ABC? Triangle DEF is twice the size of triangle ABC. All right, if you take any of the side measurements of triangle DEF, those measurements are going to be twice the size of the corresponding side measurements on triangle ABC. In example 4, they want to know if triangle ACE is similar to triangle BDE. All right, so here's triangle ACE, this triangle here, and triangle BDE is this triangle right here. We want to know if the two triangles are similar to each other. And again, we've learned that for two triangles to be similar, all they need is to have two angles that are congruent to each other. And looking at our pictures, we see that this angle A right here is 42 degrees, and this angle B over here is also 42 degrees. So they have one set of two congruent angles, but we need to actually have two pairs of congruent angles. So do I have enough information to figure out if they have another set of congruent angles? And looking at this picture, I actually see that I do have enough information to tell. All right. If I look at this entire line from A to B and this entire line from C to D, these two lines intersect at point E. And intersecting lines will always create vertical angles, and vertical angles are always congruent to each other. So this angle found right here is congruent to this angle that's found right here. Okay, they both have the same measurement. Now, I don't know what that measurement is, but this is enough for me to know that the two triangles are congruent to each other. Again, they have these two congruent 42-degree angles, and they have these two congruent unknown angles. But since the two triangles have two sets of congruent angles, the two triangles have to be congruent to each other. So I can say, yes, triangle ACE is similar to triangle BDE because two angles in triangle ABC are congruent to two angles in triangle DEF. Okay, and so that's enough for me to know that these two triangles are at least similar. I know they're the same shape, not necessarily the same size, and looking at the picture, they're clearly not the same size, but again, I do know that they are similar. Triangle ABC is similar to triangle BDE. All right, and that's actually what that should have said right there, triangle BDE, not triangle DEF. All right, BDE in our picture. All right, so now that I know that these two triangles are similar to each other, what is the length of side DE in example number 4? How much is this measurement from D to E? Okay, and it might help for you to be able to come up with that by redrawing your picture. Okay, so here's triangle BDE. I'm just going to redraw triangle ACE so that it has the same orientation. So I'm just going to draw so that it looks something like this right here. Okay, so that would be point A, this would be point C, and this would be point E right here. All right, CE right here is 4 units, okay, and AE from here to here, AE is 6 units. All right, compare that to our triangle here, all right. AE in my picture corresponds to BE in this picture right here. CE or EC corresponds to DE or ED in this picture here. So what's the measurement of DE? Well, DE corresponds to CE and BE corresponds to AE. And since these two triangles are similar to each other, I know that these proportions must be equal. Okay, so now if I fill in my the ones that I know, DE is what I'm looking for, and it corresponds to CE, which was 4, and that equals BE, which was 15, over AE, which was 6. All right, so here's my proportion that's going to allow me to figure out what the measurement of length DE is going to be. Once again, I'm going to take this ratio and I'm going to simplify it. Okay, they're each divisible by 3, meaning that I'm going to have 5 over 2 when I divide each of those by 3. 15 divided by 3 is 5, 6 divided by 3 is 2. Now I'll set my original DE over 4 equal to that. And now again, I'm trying to go from 5 to DE. So how did I go from 2 to 4? Well, I multiplied by 2. And so I'm going to do the same thing up here in my numerator. To get DE, I'm going to have to do 5 times 2, which is going to equal 10. The missing measurement on DE, this measurement right here, is 10 units, whatever those units happen to be. In our next example, we have to decide if the following triangles are similar. Explain what you know about the angle criterion. So again, I've given you some information about two different triangles in each example. I've given you the measure of two of the angles. We need to determine if the triangles are similar based off of those measurements. And again, for two triangles to be similar, all you need to have is two angles of one triangle congruent to two angles of another triangle. So here in our first example, triangle one, the measure of angle one is 45 degrees. The measure of angle two is also 45 degrees. All right, in triangle two, the measure of angle one is 45 degrees. The measure of angle two is 90 degrees. Right now, we can see that we have two congruent angles so far. All right, in angle one of each triangle, they measure 45 degrees. So we've got one pair of congruent angles in both triangles, but we need to have two pair of congruent angles for them to be similar to each other. So if I think about my triangle number one, angle one is 45 degrees, angle two is 45 degrees. Well, for angle one, all right, what is the measure of angle three? All right, well, the measure of angle three, since all three angles have to add up to 180, 45 plus 45 is 90, and 180 minus 90 is 90 degrees. So angle three in triangle one is 90 degrees. And if I look over here at triangle two, angle two is 90 degrees. So that would be another pair of congruent angles in my two triangles. Okay, so that's enough for me to know that yes, these two triangles are congruent. If I wanted to, I could also show on triangle two that the measure of angle three has to be how much? Well, 45 plus 90 is 135, and 180 minus 135 is 45 degrees. Okay, and so these two angles, all right, are also congruent. So we actually have three pair of congruent angles in our triangles. But again, we only needed to have two pair. So yes, I can say that triangle one is similar to triangle two by the angle criterion. Okay, again, I have two angles in one triangle congruent to two angles of another triangle. That's enough for me to know that these two triangles must be similar to each other. How about an example two? For triangle one, the measure of angle one is 50. The measure of angle two is 30. For triangle two, the measure of angle one is 30. The measure of angle two is 100. Are these triangles similar? Do we have two pair of congruent angles for our triangles? Well, so far I see one pair right here. All right, angle two of triangle one is congruent to angle one of triangle two, but do we have another pair of congruent angles? So triangle one this time, what is the measure of angle three? Well, 50 plus 30 is 80, and all three angles have to add up to 180, so angle three must be 100 degrees. And there it is. I found a second pair of angles that are congruent to each other. Angle three in triangle one is congruent to angle two in triangle two, so triangle one must be similar to triangle two by the angle criterion. All right, these two triangles are congruent, or excuse me, these two triangles are similar to each other because they have two pair of congruent angles. All right, how about in this third example? Triangle one has measurement of angle one is 60 degrees, measure of angle two is 20 degrees. For triangle two, the measure of angle one is 40 degrees, the measure of triangle two, or angle two is 100 degrees. Let's take a look at what we've got. Right now, I'm not seeing any congruent angles at all. So triangle one, we need the measure of angle three, and 60 plus 20 is 80, and then 80 plus 100 would be 180. For triangle two, measure of angle three equals, well, 40 plus 100 is 140, and 140 plus 40 equals 180. Okay, so the measurements of the angles of triangle one, 60, 20, and 100 degrees. The measurements of the angles in triangle two, 40, 100, and 40 degrees. Right here, they have one pair of congruent angles, but 60 and 20, 40 and 40, they don't have a second pair of congruent angles. So these triangles, triangle 1, is not similar to triangle 2. And again, we use the angle-angle criterion to prove that. We only have one pair of congruent angles in these triangles. We need to have two pair of congruent angles for the triangles to be considered similar. In example number 7, I have a picture of two isosceles triangles, and they say explain why the triangles are similar to each other. Okay, well, remember that an isosceles triangle is a triangle that has two congruent sides, and if it also has two congruent sides, then it must have two congruent angles. And those congruent angles are called the base angles. The base angles are located across from the congruent sides. And so looking at this triangle here, this is one of the congruent sides. I can tell by the markings that are on there. If you go across from that side, you get to that 70.5-degree angle right there, which is one of the base angles. Okay, and then if you go across from this missing, or this congruent side, you go across here to this missing angle, but that's the other base angle, and the base angles have to be congruent. So this is also a 70.5-degree angle. Okay, similarly, on this isosceles triangle, across from this congruent side is this base angle of 70.5 degrees, and across from this congruent side is this base angle, which is also 70.5 degrees. And now I know that these two triangles have to be similar to each other because they have two pair of congruent base angles. Okay, so the triangles are congruent. Excuse me, the triangles are similar by the angle-angle criterion. Angle-angle criterion. Okay, two angles in triangle GEF are congruent to two angles in triangle YWX. YWX. Okay, since the two triangles have two pair of congruent angles, then I know by the angle-angle criterion that these two triangles must be similar to each other. And since they're similar, I could do something to one of the triangles to scale it to be the size of the other triangle. And in fact, that's what we're going to do here in example number 8. It says, what is the scale factor that maps triangle EFG onto triangle WXY? Okay, so this is my pre-image, and I am going to map this triangle onto WXY, which is going to be the image. Okay, so what is the scale factor that maps triangle EFG onto triangle WXY? Well, what's that scale factor going to be? Let's see what we can figure out. K, the scale factor, is the image length over the pre-image length. And if I look at this example here, on triangle WXY, which is the image, I know that YX is 2, and that corresponds to GF on the pre-image, which is 6. So the scale factor is 2 over 6, which simplifies down to 1/3. K equals 1/3. So triangle WXY is 1/3 the size of triangle EFG. Okay, so again, to find a scale factor, take a length from the image over the corresponding length of its pre-image, and then simplify down. 2 over 6 simplifies to 1/3. WXY is 1/3 the size of triangle EFG. Now determine the length of side WX. How much is this length right here? Well, WX corresponds to EF, which is 9, And that has to be equal to another ratio of corresponding sides. In this case, we can again use 2 over 6, 2 on the image to 6 on the pre-image. And we said before that 2 6 simplifies down to 1/3. So we could say that Wx over 9 equals 1/3. And now I always want to move toward my unknown. So how would I go from a 3 to a 9? Well, I would have to multiply by 3. So to get the length of Wx, all I'm going to do is do 1 times 3, which is going to be 3 units. Okay, so this missing side on triangle WXY, Wx measures 3 units.